Today's S lecture is on the derivation of Bayes' rule in both the discrete case and the continuous case. Before we derive Bayes' rule in the discrete case, there are some parameters we need to define. First being the prior of class I, which would be defined as probability of Wi, and then there's the class probability or conditional, it's also called the conditional probability, which will be defined as probability of x given omega I, and then the mixture probability of the set, the data set, which will be defined as probability of x as a vector. We derive Bayes' rule through Bayes' theorem, and the definition of Bayes' theorem is posterior probability will equal the likelihood times the prior over the estimation. This is Bayes' theorem. Now, in the discrete sense, given two random variables, x and y and z, the probability of z given y equals the probability of y given z times the probability of z, or the prior of z, summation of the probability of y given z times the prior z, probability c. To derive Bayes' rule, from Bayes' theorem, we have to first have a set of properties, or define a set of properties. The first property is probability of y will equal the summation under z, probability of z and y. And second property is the probability of z and y equaling the probability of y given z and the probability of z. The probability of y and z, probability of y and z equals the probability of z given y times the probability of y. With properties 2 and 3, we can derive a fourth property saying the probability of y given z times the probability of z equals the probability of z given y times the probability of y. Taking property 2, we can take Bayes' theorem's equation and change the bottom, the denominator, with property 2, making it the probability of z given y equals the probability of y given z and the probability of z over the summation, the probability of z and y. Now, we know the summation, probably z and y, from property 1. So then that Bayes' theorem becomes equal to probability of y given z times the probability of z over the probability of y, and that gives us Bayes' rule for a discrete set of data. Now for the derivation for the continuous case. So assume x, vector in x, x1 through xn is a random vector. Remember, this is for the continuous case. We are deriving Bayes' rule. So x bar is a random vector with values in Rn, and x is characterized by a PDF, probability density function, P of x bar equals to P of x1 to xn, or equal to probability x less than Now, for the classes, each class has a conditional density probability. So it would be P of x given Wi. This can be also called the class density. Now, we again recall Bayes' theorem is the probability of Wi given x bar is the prior Wi over the summation of P of x bar over Wi, the prior of Wi. Now, to implement Bayes' rule, we must say, given to implement Bayes' rule, given x bar is equal to x bar, decide Wi if, or decide the class of x if the probability of Wi given x is greater than or equal to probability of Wj given x for all j from 1 to c. Therefore, we take Bayes' theorem and we say probability of x given the class with the prior of class over the summation of the probability of x given class L, prior of class L equals 1 to c, is greater than or equal to the probability of x given Wj, Wj over the summation of L. So I just expanded Bayes' theorem Now, since the denominators are equal, we can cancel these out, giving us the probability of x given wi times the prior and the greater than or equal to the probability of x given omega j prior of omega j for all j. So, for the continuous case, given an x, choose a class such that the probability of x given the class times the prior class is greater than the other class. So, for instance, if I have a data point that has a higher probability in this class than this class, then I classify x bar with wi. And in another case, if the probability of x given wj is greater than the probability of x given wi, then I classify x in wj. And that was the Bayes rule for the continuous set. Thank you for listening to this S lecture.